I'm Akshat Nair. I'm an engineering manager on the data platform organization at DoorDash. With me today, I have Satya with me. Satya, you want to introduce yourself?
Yeah, sure. Hey everyone, my name is Satya. I'm here on the analytics engine team working on our data lake and Trino efforts.
All right. So today we'll be talking about our journey on how DoorDash started using Trino for our data processing needs. So we will be covering various topics today. Satya, can we get to the next slide? Thank you. So yeah, we'll talk about what is DoorDash for the folks who are not aware about our company, the current data ecosystem before we started using Trino, why we decided to go towards a data lake setup, and for that, why did we choose Trino for our query processing needs. And then Satya will cover about how we are deploying Trino in our environment and what are the next things that we're looking forward to implementing in our systems. Next slide. So what is DoorDash? So DoorDash is a mission. DoorDash's mission is to grow and empower local economies. How we do this is by connecting people to the best in their local communities. DoorDash serves millions of consumers by connecting them to hundreds and thousands of merchants, and this is done through our logistics platform. Next slide. So before we started using S3 as our data lake, this was how our ecosystem looked like. We had data being ingested from various third-party systems and our production databases using our custom Python ETL code. We were running this orchestration on Airflow, and we were ingesting this data into Snowflake, then running some SQL transformations through Airflow as well on top of this data in Snowflake and generate the transformed data sets and store them again in Snowflake. This dataset was then being queried and processed by our various teams within DoorDash through dashboarding systems like Tableau or Chartio or through ad hoc SQL queries. Next slide, please. So what were the shortcomings that we had in this system? One of the problems that we would see is that we had to load this data into Snowflake before anyone could access it. This added a little bit of latency, especially for the cases where we had real-time query needs. The second problem was where we had our machine learning jobs that were running in Spark, and they had to pull data out of Snowflake to query and process it. The Spark Snowflake connector was unfortunately not performing to the performance capacity we needed it to perform. And this led us to also think that, okay, maybe we need another way of getting this data into our Spark jobs so that we can speed them up. The third problem was the historical or archived data storage. For most of our event data that was coming in, we were storing all of it into Snowflake. And this data was in terabytes and petabytes. And with the growing needs of data in the company, we were ingesting more and more such events. And if you're not actively removing this data from Snowflake, querying it was becoming a problem because you had to ensure that the proper clustering was in place and people were querying it with proper filters on it. Otherwise, it would waste a lot of compute resources and also the bandwidth for other users to use the warehouse at that time. The fourth point was the ability to join with other sources like Apache Pinot. We had adopted Apache Pinot as our OLAP system, and if we had to join a data set in Snowflake with a data set in Pinot, that was not feasible in the current setup. So we started looking for various options, and these were the options that we considered. Next slide, please. So before we get into the options we considered, let's look at how the current setup looks like at DoorDash. We basically are still ingesting our transactional data and some event data into Snowflake for our ETL batch processing needs. But we are also ingesting this data from Kafka into Flink and getting it into our data lake in S3. And some of this data is also going into our Apache Pinot setup. And our users are able to query data from Snowflake, data from S3, and data from Pinot using Trino. And we are in the process of setting up our dashboarding systems as well to increase our usage rather than just using it for ad hoc usage. We're also going to start using it for reporting purposes. So our ETL transformations are still happening within Snowflake, but our raw event data is now landing into S3, which is helping us to run some machine learning jobs and other data processing on top of it in a much faster way compared to what we could do before, because we had to pull this data out of Snowflake, then get to S3 and then process it. We are also dumping some transformed data sets from Snowflake into S3 as well, because there are multiple Spark jobs that need this transformed data for their processing. So we have a process where we copy this data one time into S3 to make it faster to run it on Spark. Eventually, we are hoping that with Trino, we will not have to do this data copy as well and use it in the place where it's being generated, which is Snowflake, and just join it, combine it, and run maybe ETLs at some point in time on Trino setup. Next slide, please. Once we had decided that we needed to copy this data into S3, we actually considered various options before landing on Trino. The options we considered were Snowflake external tables, Trino, and Spark SQL. The Snowflake external tables was actually intuitively the most, we thought that this will be the system that will actually work the best for us, because it would make it easier for us to continue querying within Snowflake. We didn't have to change any, data connections and things like that, and we could continue querying all of our data set from the Snowflake interface. But the problem we saw the most was querying the external tables on S3 from Snowflake was really, really bad in performance compared to the other systems that we had. And also, we couldn't connect to Pinot from Snowflake interface as well. So that was one drawback that we saw with Snowflake external tables. Then we tried out Trino. The benefits we saw was definitely query federation, because we could connect to the data that was already in Snowflake, we could connect to Pinot and to data that was in S3, and we did not have to move any data between the systems to query them. And the biggest advantage was also that it was ANSYS SQL compliant, so we didn't have to change any of our queries substantially. We also considered Spark SQL for this ad hoc usage, because we are already using Spark for some machine learning jobs. We wanted to see if we can unify all of this usage for the ad hoc users as well. It was definitely the fastest systems to query S3 with the Delta Lake setup we had. But the problems we saw was that SQL access was not standard, and the Snowflake Spark connector had the same issues. So anytime we had to join data between S3 and Snowflake, we would run into the same performance issues. Also, there was no access to Pinot, and eventually we are looking to add more catalogs. And we thought that using Trino as a pluggable system where you can add more connections to newer systems that we are trying to do, maybe eventually our production systems like Postgres, would be a win-win situation for us. Next slide. Now I'll hand it over to Satya to talk about how all of this deployment about Trino is happening in our ecosystem.
Awesome. Thanks, Akshat. Hey, everyone. In this section, I'll briefly cover on how we are deploying Trino at DoorDash. And before I jump into how we are deploying it, I want to briefly cover the various components we deal with in Trino. First one being the coordinator, basically, which is responsible for parsing the query, planning, and managing the workers. The second part is the workers, who are basically doing the heavy lifting in terms of like fetching data from various tasks, processing it, and basically ultimately executing the tasks. The third one is the meta store, where we are actually storing all the information about the databases, schemas, tables, your partition metadata, and things like that. And the fourth part is actually the data sources, like, or the catalogs as we call it. These could be like multiple data stores or sources of data we have, and the various connectors we need to use for them. At DoorDash, we are for the meta store, we are using the Glue catalog. There has been definitely conversations around the performance on the Glue catalog, but so far with our usage, it's been working out okay for us. But switching to Hive Metastore is something on our mind. We'll probably do that in the future when we get to that scale. On the catalog side, we are basically connecting to 3 of these sources right now, and plan to add more in the future. And for the purpose of this talk, I'll mostly focus on how we are deploying coordinator and the workers on Kubernetes. So why Kubernetes? The very basic question, right? Like, why not as a plain EC2? We are completely an AWS shop. Why not deploy on EC2 or something else? Uh, First thing is basically Kubernetes is the matured compute platform at DoorDash. Every single microservice we have is being deployed on Kubernetes. So when we were talking about deploying Trino, it became the obvious choice with the amazing support from our compute platform. The deployments are much faster compared to like having Trino run on EMR, things like that. Those are definitely slower compared to Kubernetes. Scaling is another aspect. We don't really have to worry about scaling. It's already taken care. And the failover strategy. So anytime you're working with Trino, most of you are probably familiar with the worker failure, and then you need to like relaunch it or take care of it manually. But with Kubernetes, that is something taken care of for you. So it's much easier to scale in a way. And the third part is like, so the way we are doing is we are having different clusters. So basically, we are separating these clusters based on the team, based on the usage patterns and things like that. So, for example, a Tableau might have its own cluster compared to some ad hoc analysis or Spark analysis or things like that. So we are separating these clusters. So anytime we want to launch a cluster, it's as simple as just adding a config and then pushing it out. It's that simple. Uh, so how we are deploying on Kubernetes? Obviously, there are multiple ways to do it. You could use kubectl or Spinnaker or Helm, and we chose Helm. Again, this has been widely used across the org. It became the obvious choice. So we are deploying using Helm. When it comes to Helm, I want to cover basically the three core pieces of it. One is the Helm charts, where you're basically storing all your files that describe the related configuration for the application. So this could be various YAML files which are grouped together and can be reused again and again in multiple places. The second part is the Helm release, which we use quite a bit. I will get to it in a bit, but it's basically an instance of a chart, and you could have multiple Helm releases at any given point of time. And the third part is the Helm operator. Once you have these charts and the Helm release, how is it actually pushed out to the cluster? So that's where Helm operator comes in and takes care of all the changes that needs to be done for the deployment. So let's see what the Helm chart is. Basically, so you see on the left here, it's basically a set of files grouped together describing your application. The very basic one is the chart YAML, where it contains all the metadata about your chart. In this case, it has basically the very simple repository information, and we are also using the Starburst Enterprise Edition of Trino. So basically, we list that as a dependency here. So our chart, this file is basically a wrapper to the Starburst chart. The next part is the values. So this is where usually like we tend to, when you're installing the Helm chart, this is where you tend to put all the information corresponding to your cluster, how to scale it, anything, all the related information. But we use values YAML as just a placeholder for the config. So nothing is actually going in here. We will have all that information in the Helm release to make it easier, because every cluster might have a different configuration. So having that information here doesn't really work. So we decided to put all that in the Helm release, which I'll get to in a bit. And the third part is the secrets. Basically, we are having the secret parts in the templates because most of our clusters do need these secrets, and they're automatically generated for every cluster and passed on to the Kubernetes. Coming to the Helm release. So this is where the crux of the configuration is. So you can see that basically this is where we are defining all the values. As an example here, how are the secrets being fetched from the vault? For example, Snowflake credentials or Kafka or things like that. They're all basically fetched from the vault in this case. And you also have the chart information. You also have the chart information here. So you can see that basically this is referencing to the master branch of the chart. And secret annotations, basically defining our vault configuration and things like that, the URL and the username and password, and all the cluster configuration is actually specified in the Starburst Enterprise section. So let's see what the coordinator part looks like. So right, like you could have drop in these files, the etc files, the log properties, and anytime we want to inject any environment variables, basically they are basically pushed from the secrets, which are defined in the secrets YAML which we just saw. And again, the resources are pretty standard here for the coordinator. So for the workers, this is where things get interesting, right? So we pretty much have the environment variables as we defined earlier. Uh, and if you look at the auto scaling, this is where it comes in handy. We do have the auto scaling enabled. You specify min and max replicas, and depending on the load and the CPU usage, basically Kubernetes will take care of like scaling up the cluster or scaling down the cluster, which is working out really well for us. Well, we also have the shutdown grace period for these workers because anytime you're scaling down, you don't want the queries running at that point to be abruptly shut down. So basically, we set the grace period to 2 minutes. We also have the deployment termination grace period set at 5 minutes. And as usual, you also specify the resources for each node in terms of like the CPU and the memory, what to assign. So how do we handle the upgrade? So this is the neat part. Has been working out really well for us because we are using the releases. We are using the Helm release. Anytime you want to change, basically it's, for example, recently we did a major upgrade from 348 to 356. So basically at that point you change your chart, the Helm charts, uh, on a different branch. So the master is still on 348. You have your Helm charts with all your changes corresponding to 356, and your staging Helm release is actually pointing to 356 here, whereas your production is still pointing to master. So this gives the flexibility to test things in staging before being pushed to production. And once everything looks good, we are basically using the same chart for both staging and production. So once we have these files, I want to get into like, okay, how are these actually being deployed to the cluster? So anytime someone commits a change to the Helm release, we use the Flux CD and the Helm operators to get the changes out to the cluster. Flux is again, which enables the continuous deployment. It's basically a GitOps for Kubernetes, which is amazing, which working out really well. And it basically syncs all your CRDs, the Helm releases, to the cluster. And at that point, the Helm operator compares the current deployment and basically the requested change, and it makes the changes accordingly. And if something goes wrong, obviously that deployment will be stopped, and you can actually see the status of the Helm release and look at like why things failed and things like that. So it's a very nice way of deploying so that you're not actually bringing down the cluster when you're doing these deployments. The last part is the catalogs. Right now, we are using connecting to these three catalogs at the moment. Snowflake, where we have all the fact, dimension, and other production data, transactional data coming from these production tables. As Akshat mentioned, we are also using Pinot at DoorDash, and Trino is becoming basically the primary queryable interface for this tree for the Pinot data, and then we can connect with Snowflake or data from S3. And the last part is a Hive connector, which we are using actively to query this data stored on S3 in a Parquet format. The future work, obviously, we want to look into the Presto Gateway, as it is. I think it's still called Presto Gateway, as a load balancer in terms of like routing these queries, or anytime we want to take the cluster offline. So we'll eventually like have that in front of our clusters. Ranger integration is one thing we are actively looking into to support role-based access control. Um, and the data mesh. Obviously, we have a very limited data sources at this point. We also want to connect Kafka, for example, so that users can see or derive any sort of like key metrics in real time from Kafka if they need to. So that's all I have. Akshat, do you want to wrap it up?
Yes, thank you, Satya. No presentation of mine will be complete without a shameless plugin for hiring needs. DoorDash is hiring a lot and my team is growing. And if you found any of this work exciting, do come join us. You'll get to work with Satya on all of these things and much more. You can reach out to me or Satya on our emails or connect us on LinkedIn.